This is our review for area and volume problems. Volume just by revolutions, or the washer-disk method. Problem number 1. Write the definite integral that represents the area of the region enclosed by y equals 4x minus x squared in the x-axis. So we'll start out with a little sketch of this so we know what it looks like. 4x minus x squared is a parabola that has x-intercepts of 0 and 4, and the x-axis, well, is the x-axis. So we're looking for the area of this region, and that's simply going to be the integral from 0 to 4 of 4x minus x squared with respect to x. For those of you that like doing top minus bottom, that is exactly what this equation is. It's the curve 4x minus x squared minus the bottom curve, which is y equals 0. Number 2. Find the area bound by, it looks like almost the exact same equation, 4 minus 4x squared. So this is a upside down parabola with intercepts at -2 and +2. And y equals 0, which is again the x-axis. So we're looking for this area in here. And again, we're going to do the integral of 4 minus 4x squared from -2 to 2. And just drop that in your calculator for the answer. It is possible on graphs like this, and by like this I mean graphs that are symmetric, to only do half of the integral and multiply by 2. In other words, we will get the same answer if we integrate from -2 to 0, 4 minus 4x squared. That gives me the shaded region, but then multiply by 2 for the entire region. Both ways work. Whatever way appears to be most convenient for you is the way you should do it. Find the area of the region in the first quadrant bound by the graph of e to the -2x and y equals 0. E to the -2x looks like this. It's asymptotic with the x-axis, so it's never actually going to have an x-intercept, which means when we're doing our integral, our bounds are going to be from 0 to infinity. And we know this starts at 0 because it says the first quadrant. So we're going to integrate e to the -2x. This is some u sub, so we're going to let u equal -2x. du then is -2 dx. So our integral is going to be e to the u du. When doing u sub, and I know it's been a while, but when doing u sub, we do need to change our bounds. These bounds up here, this infinity and the 0, are both x's. To change them into u's, we simply take those two bounds and we plug them into our u equation. We plug them in as x's to find out the u values. And when you plug in 0, you get 0. When you plug in infinity, you get -infinity, which might make you feel like you're doing the problem wrong, but it will work out in the end, I promise. Integrating, I missed. Our du was -2, which means we need to have a -1/2 out there. That was close. Okay, integrating that gives us -1/2 e to the u evaluated from 0 to -infinity. To evaluate this, we plug in -infinity, and we plug in 0. E to the -infinity is effectively 0, and 0 times -1/2 is 0. So that entire first part is just 0. minus a negative 1/2, which can become plus 1/2 times e to the 0. E to the 0 is 1. Final answer then is 1/2. The next one, from 0 to pi halves, find the area of the region between the curves cosine and sine. Okay, so we are looking from 0 to pi halves. Cosine starts at 1 and descends as we go toward pi halves, where it hits the x-axis. Sine starts at 0 and ascends to where it hits 1 at pi halves. That is a horrible drawing. This should be symmetric. These two areas should be exactly the same. Generally, we find the area between two regions by doing the top curve minus the bottom curve. But on this problem, you'll notice that the top curve on this side is the cosine curve, but the top curve on this side is the sine curve. And that means we're going to have to do either two integrals here, or because it's symmetric, we could do one side and then double it. So the big question before we set up our integrals is, where do these two curves meet? When does sine x equal cosine x? This is where 15 minutes at Whataburger looking at your unit radius circle will really pay off. They meet at pi fourths. So our integral is going to be from 0 to pi fourths the cosine of x minus the sine of x. And then our second integral is going to be from pi fourths to pi halves the sine of x minus the cosine of x. Drop that in your calculator and you're done with the problem. You could, if you wanted to, from the first half of this equation, just integrate this and then multiply it by 2. And that would also give you the region. Whatever is most convenient to you. If you're really nervous and have a lot of time, calculate the area both ways just to verify your answer and build your confidence. Number 6, finally a volume problem. Keywords in knowing it's a volume problem. Volume. We're looking for a solid, not just an area of a region. And these are all going to be created with revolutions, which means we are creating circles. So every single time you're looking at a volume created by revolution, your formula is going to be effectively the integral of pi r squared. If it's rotated around a horizontal line, it'll be dx. If it's rotated around a vertical line, it'll be dy. Well, you might have a chance to look at those later. Most of the problems on the test will be rotated around a horizontal line, so they'll mostly be dx. And this one is exactly that. So, our region, or our solid, is formed by rotating y equals 2x. That's that line. Y equals 0. That's, probably do that in a different color. That's the x-axis. And x equals 1. Now you can imagine when we rotate this what kind of a shape it's going to create. It will create something that looks like this. We call that a cone. In fact, you could find the volume of this problem simply by using the volume of a cone formula 1/3 pi r squared h. But that is no fun. It's way more fun to integrate. So, the question is, on this cone, what is the radius, since we just have to integrate pi r squared? Well, the radius of any circle we pull out of here, I'm just going to sketch on a little circle to be cut right out of the middle of this thing. The radius is the distance from the x-axis up to the curve. That distance right there. How far is that? Well, that depends on where we are on the x-axis. But that height is always determined by the function y equals 2x, which means your radius is always 2 times the x value, whatever x value you're on. So this integral is going to be pi times the integral of 2x, which is your radius, squared, as x moves from 0 to 1. 0 and 1, the lowest x value to the highest x value. And both those things came from the region. X equals 1 is this high end here, and x equals 0 is where these two graphs, 2x and 0, intersect each other. Those are the x values of basically the 2 points of intersection of the graph. Drop this in the calculator, and I'm so sorry I don't have mine here with me, but drop that in the calculator and it should yield your answer. Number 6. We're going to find the volume of the solid form by revolving x plus 2 to the 1/2. Okay, that's going to be a square root curve that's shifted over to the left 2. And we're going from -1 to 0. So you can imagine this thing, hopefully, when we rotate it, we'll have some shape like this. It is really hard to draw on here. But a lot of these shapes are very difficult to represent in 2 dimensions anyway, because they're so odd. I tried to draw this blue line, the axis of rotation through there. Okay, so this again is just pi r squared, and our radius is going to be, well, however far that is. And that distance is from the x-axis up to the curve, and the curve's that line, or that function. So x plus 2 to the 1/2 squared. Drop a pi on the outside, and we're going from -1 to 0. I would simplify this before dropping in your calculator. You could put it in just as it is, but notice that you have a 1/2 power and a squared power. Those are going to cancel out, and this is going to be exactly the same as just -1 to 0 of x plus 2. The hardest part of these problems for most people is just recognizing what your radius is. And for most of these problems, the radius is simply going to be the distance from the x-axis to the curve, which is always just going to be the function value. If we move our axis of rotation off of the x-axis, suppose we were going to rotate this exact curve around the line x equals -1. Well, if we were to rotate around x equals -1, our graph may still look the same. That's a square root of x plus 2. But if we're rotating out around this axis, down here at -1, then our radius of rotation is going to be that entire distance, which ends up being the square root of x plus 2 minus -1. Always top minus bottom will give you the distance between 2 points. Number 7. The region bounded by the graph of f of x equals x times 2 minus x is revolved about the x-axis, the volume of the solid. Okay, so look at that. It's already factored for us. You can tell it's a upside down parabola with intercepts at 0 and at 2. So there's the region we're looking at. And we're going to rotate that around the x-axis. So you can imagine this shape as being kind of an elongated ball when that's rotated around the x-axis. And we're just going to do the integral of pi times the radius squared. The radius is the distance to the curve, which in this case is just x times 2 minus x. If you want to distribute that x because you like the way it looks, then distribute that x. You're the mathematician in charge of the problem. Do it the way you like. Notice I'm squaring it because it's always pi times the radius squared. And this is for all x values from the least x value to the biggest x value. And our smallest x value is 0, and the biggest x value is 2. And so this equation is really just adding up the areas of every circle that could be created from 0 to 2. When looking at number 8, you may not recognize this graph. X to the 1/2 plus y to the 1/2 equals 3. That's certainly not a common parent function that most students will recognize right away. So I'm going to do this one, pretending like I have no idea what this graph looks like. Well, I know that I could get y all by itself. Let's see, that's going to be this y to the 1/2 equals negative x to the 1/2 plus 3, which means y is going to equal, I'm going to write it as 3 minus the square root of x squared. So the height of my curve is always going to equal this thing. If you're worried about this and need a sketch, I'm going to sketch something that does not look like this graph at all. We'll just make it some crazy graph. And I know we're looking from 0 to 3. And as this thing rotates to form a solid, this crazy shape I made is going to look a little bit like a vase. All we have to do is the integral of pi times the radius squared. Well, what's the radius? The radius is the distance to the curve. How tall is that curve? Well, that curve is 3 minus the square root of x squared. And we're going from 0 to 3. At this point, I've done one thing wrong, other than forget my dx. Can you tell what it is? I hope you noticed that I did not square my radius. Be careful with these problems. The squared that you see written here, right there, came from what y equals. That's part of my equation. So that squared, here in green, is part of the radius. We have to do pi times the radius, that whole thing, whatever it is, squared. Drop in your calculator and you're done. Alright, find the volume of the revolution by maybe I copied this problem wrong. Ignore the terrible grammar. But we understand what the problem's asking. So let's draw this thing. We've got x to the 1/2, which is square root of x. X equals 4. And y equals 0. A very easy region to understand. And now we're going to rotate this. This problem is different than every other problem we've done because we are finally rotating around the y-axis. This does not change the equation though, except this one, when we revolve it, will also have a hole in it. Now we haven't had any on this review yet that have had holes, but you'll hopefully be able to imagine that when this thing revolves, we've got a very solid region here, but an empty space in this area. It looks like maybe a cylinder with a Hershey Kiss removed. Well, let's get started on this thing. You'll see that if I were to take cuts of this thing to examine the circles, well, all those circles are going to be stacked on top of each other this way, which means the width of each disk we're taking out is a small change in the in the y-axis, which means these things are going to be a dy. Now, because there's a hole in it, we use the formula r squared minus little r squared, where big R is the distance from the center of rotation out to the outer curve, and little r is the distance from the center of rotation to the inner curve. Okay, I'm going to toss on a dy here, just to keep in mind that everything needs to be in terms of y. We can't integrate the square root of x with respect to y. We need to integrate a function of y with respect to y. So let's change that. Instead of y equals x to the 1/2, we're going to say x equals y squared. Do whatever simple algebra you rock at to change the equation from something in terms of x to be something in terms of y. Okay, well, that's basically all we need to do on this thing. Let's set up the equation. We've got pi times, now the big radius goes from the center of rotation out to the outer curve, and this outer curve is entirely defined by x equals 4, which means your big radius is going to be 4. Regardless of what your y value is, your big radius will always, on this problem, be 4. So, big radius squared is 4 squared, minus, now my little radius does change, and my little radius changes in this form, x equals y squared. So, y squared is my little radius. Don't forget to square it, because you've got to do r squared. And this is with respect to y. Drop that in your calculator, and you're done with the problem. As I embark on this last problem, I realize I copied it wrong. This equation should be y equals 2 minus x times 2 plus x. I am so sorry. I will not do this problem written here. Instead, I'll do the one on the review, which is this thing. If you'd like to multiply it out first because you prefer to see the quadratic unfactored, then by all means do it. You're the mathematician in charge. 2 times 2 is 4. Oh, it's a difference of squares, so we end up with 4 minus x squared. Same equation. I personally would prefer to use this one because it's a little less to write. The nice thing about the factored form is it does show us our x-intercepts. If we want to get a nice accurate graph, our x-intercepts are going to be at 2 and negative 2. And the other equation, y equals 3x, is just a line that goes through there. We're looking at rotating this region around the x-axis because it's rotating around a horizontal line. Then I know that my equation is going to be an integral in terms of x. I also know that this is going to have a hole in it. So it's going to be big R squared minus little r squared. Drop a pi on the outside. We do need some boundaries here. We'll do the boundaries in a second. Let's go ahead and write the whole equation in there. We have pi times the integral of, now my big radius goes from the center of rotation up to the outside curve, which means my big radius is going to be the distance 4 minus x squared. Don't forget to square it. And my little radius goes from the center of rotation up to the line 3x. So it's going to be minus 3x squared. Be very careful when you're putting things like this in your calculator, if you're doing this whole thing on the calculator. Be careful that your squared is outside of your little radius. If you put the squared only with the x, then it's going to throw off your entire answer. Okay, the boundaries here. Let's pretend for a second that you did not have your calculator, as I have no calculator right now. To find out where these two graphs intersect, we're just going to take 4 minus x squared and set it equal to 3x. This is how we're going to find this upper boundary where they intersect. To solve this, we want to factor it. So we're going to move our x squared over to the right side. That'll give us x squared plus 3x minus 4, which factors into x plus 4 times x minus 1, which means these graphs intersect at negative 4 and 1. Our boundaries then are going to go from 0 to 1. The negative 4 doesn't quite enter into it. To see where they'd intersect, we'd have to extend this curve down here and extend the line, and there and intersect back here. That's where the negative 4 is going to be. But the problem does specify that this whole thing is to be done in the first quadrant, which means we are definitely limited to just this top right quadrant. Anyway, that's that whole thing. Just drop this equation in your calculator, and that should give you the answer. If you need help with the calculators, please come by tutorials. With a lot of these problems, the hardest part is recognizing the shape. So sometimes just don't bother drawing it, don't bother writing the numbers, don't bother thinking about the equations. Just imagine the shape and see if you can visualize what it would look like when it's revolved around some given axis. Good luck. I'll see you in class.